So in last video, we learned that the sample average, when you center it around the population expectation and scale it by square root n over the standard deviation of the population, the new random variable that you obtain converges in distribution to a standard normal random variable. Or you could also say this random variable converges in distribution to standard normal. Convergence in distribution, as we have learned, means that the convergence of the CDF. So the CDF of this random variable converges to the standard normal CDF at every point. So when a sequence of random variable converges in distribution to some other random variable, we say that the distribution of this random variable z, which we call the limiting random variable, is the asymptotic distribution of the sequence Zn. So when Zn converges in distribution to Z, then the distribution of Z is the asymptotic distribution of Zn. So that's what the term asymptotic distribution means. Or sometimes I also say limiting distribution. It means the same thing. It means the same thing as asymptotic distribution. So the central limit theorem tells us that the asymptotic distribution of this transformed sample mean random variable is standard normal. In other words, we can also say this random variable is approximately distributed as standard normal when n is large. And we use this notation to denote this approximately distributed by when n is large. So this is approximately distributed by standard normal when n is large. In this result from the central limit theorem can be used to calculate probabilities regarding events about x n bar, or about n times x n bar, which is the sum of the x in the sample. Okay, so let's consider some examples where we can do this calculation. The first example considers Bobby, a customer service agent. She needs X minutes to serve one randomly select customer. So X is the number of minutes she needs to serve one random customer. Suppose, based on very long-term observation of Bobby, we know the expected value of X is mu, and the variance of X is 1 minute. Standard deviation is 1 minute. Variance doesn't have that unit. So now we know the expectation is mu and variance is 1. To serve 100 customers, what's the probability that Bobby needs more than this many minutes? What's the probability that Bobby needs 25 more minutes than the expected number of minutes? So we can do this calculation. First, we can use xi to denote the number of minutes needed to serve the ith customer. And suppose the customers are independent, then the total amount of time you need to serve these 100 customers is the sum of the time needed to serve each. So here, x1 plus x2 plus xn, this sum when n equals 100 is the time needed for Bobby to serve 100 customers. So what we want to calculate is this x(t) probability that this sum total time is greater than 100 times mu plus 25. Notice that in the example, we don't know what the distribution of x is. We don't know the distribution of x. We only know the expectation and the variance, but we don't know the distribution of x. Therefore, we also don't know the exact distribution of the sum. However, the sum is n times the sample average. Right? So that is n times the sample average. And for the sample average, so this event can be written as an event about the sample average. So which is xn bar greater than or equal to mu because n equals 100 plus 0.25. The distribution of xn bar is approximately normal when n is large. Let's say n equals 100 is pretty large for most distributions of x. So we want to use that normal distribution to approximate this probability. So in order to do that, we want to create this xn bar minus mu, this recentered variable on this left-hand side of this inequality. So that's greater than 0.25. And we want to also multiply that by square root n, which is 10 in this case because n equals 100, greater than 2.5. And the variance of x is 1, so sigma equals 1. Therefore, this is in fact square root n xn bar minus mu divided by sigma. So this is approximately distributed as standard normal by central limit theorem. Therefore, this probability is approximately the probability that a standard normal being greater than 2.5. Standard normal, let's use z to denote the standard normal random variable. Where z is the standard normal random variable. And this approximately equal sign is due to the CLT, the central limit theorem. Now, because now this z has a known distribution, it is standard normal, we can calculate this probability already. So that probability, we can look up that probability in the normality table that we have looked at before. So this is the normality table that we have looked at before. So this table, all these cells give you the probability that the standard normal random variable is between 0 and the value z, where the value z is given by these columns and the rows. So up to the first decimal point is given by the columns, and the second decimal point is given on the rows. So what is relevant for us is the z equals 2.5. Right, so for z equals 2.5, we look at this row and the column being corresponding to the zeros because there is no second decimal point. So therefore, what's relevant is this probability, 0.4938. So probability, so this table tells us that probability z is between 0 and 2.5 equals 0.4938. So this is actually an approximation because the actual probability has more digits than 4, but the approximation is quite good. So probability of Z being in this area is 0.4938 when Z is 2.5. The probability that we look for is probability that Z being greater than 2.5. So it's actually this little area. And we know for the normal distribution, the standard normal distribution is symmetric around 0. So the probability of being in this half of the real line is 1/2. Therefore, the area under this portion is 1/2 minus 0.4938. So that should be equal to 0.5 minus 0.4938. So that's equal to 0.0062. Right, so 0.0062, yes. So the probability that Bobby needs more than 25 minutes more than the expected amount of time is very small. It's about 0.62%. So that's how you calculate the some relevant probabilities using central limit theorem in this example. Let's consider another example. Suppose that X is Bernoulli distributed. So X is a dummy variable that takes the value 1 and 0, takes the value 1 with probability P, and takes the value 0 with probability 1 minus P. Now let's consider actually this concrete example. Suppose that X is the dummy variable indicating the sex of a newborn baby. So if the newborn baby is boy, if a randomly selected newborn baby is boy, then X equals 1. If that newborn is a girl, then X equals 0. X for that newborn baby is 0. So X is the dummy variable for the sex of a randomly selected newborn on, say, an island. If suppose that P equals 0.5, that is close to the natural sex ratio at birth. So half of the newborns are boys, half of the newborns are girls. Suppose that P equals 0.5, okay? Then what is the probability of observing a sex ratio greater than this much among 210 newborns? Suppose that there have been 210 newborns in the past 2 years or something, and you observe 110 boys and 100 girls. What is the probability of, I'm sorry. So next, let's consider an example where X is a Bernoulli random variable with success rate P. Let's make it concrete and consider that the case that X is the sex dummy variable for a randomly selected newborn on an island. X equals 1 if that newborn is boy, and X equals 0 if that newborn is a girl. So X is a dummy variable indicating the sex of that newborn. If the true success rate, the true probability that the newborn is a boy is 0.5, that is close to the natural rate of boys among newborns for uninterrupted for a natural population. So suppose that P is 0.5. Then among 210 newborns, suppose there have been 210 newborns in the past year or so, what is the probability of observing a sex ratio among these newborns that's greater than 110 to 100? So what is the probability of observing a sex ratio greater than this ratio? Now, how do you answer this problem? So first, we're gonna write the problem in mathematics. So with 210 newborns, that means we have an IID sample with n equals 210. And this is an IID sample from Bernoulli 0.5, and n equals 210. And the event we are interested in is the event that the average value of this Bernoulli random variable, actually, the event is more directly written as the sum of the x variables, which is the number of boys among these 200 newborns, right? So this is the number of boys, because x equals 1 when the baby is when the first x1 equals 1 when the first baby is a boy, and 0 otherwise, and the same thing for x2 to xn. So therefore, the event we are interested in is regarding the sum of these Bernoulli random variables. The sum of these Bernoulli variables is the number of boys. And we want to know the probability that this is greater than 110. So because we know the true distribution of the data, we know all the x are from Bernoulli 0.5 distribution. We also, in principle, know the distribution of the sum. This is the number of successes, success being defined by being a boy. That, according to what we have learned in one of the videos, this sum is a binomial random variable. This sum follows a binomial distribution. Let's say this is Sn, follows a binomial distribution with parameters n, which equals 210 in this case, and p, which equals 0.5. So this is a binomial distribution. Binomial distribution is a discrete distribution that can take value from 0 to n. And we actually know the formula for the PMF. So the PMF of this binomial distribution is in fact n choose x, p to the power x, 1 minus p to the power n minus x. We actually know this PMF. Therefore, this probability in principle can be written as a sum of these PMFs. So in principle, it can be written as sum of x from 101 to 210, n choose x, p to the power x, 1 minus p to the power n minus x. This In principle is a known quantity because there is nothing unknown about it, nothing unknown in this formula. However, it is very hard to calculate. The reason is when n is 210 and x is 111 or numbers close to it, this n choose x is a very large number. It's actually a really large number. It's quite hard to calculate. And even if you can calculate this one by one, you have to calculate 100 times in order to get this sum. So it's difficult, even though you know the distribution of the sum, which is binomial, it is hard to calculate it directly using the known probability mass function. Known in principle but very hard to calculate. Even if you have a computer, it's hard to calculate this number to a good accuracy. On the other hand, we can use the central limit theorem to approximate this distribution, and that will be much easier to calculate. So how do we use central limit theorem to calculate this? Probability that this sum as n being greater than 110 equals the probability that xn bar, which is the average of the x in the sample, of the Bernoulli random variable in the sample, being greater than 110 divided by the sample size n, which is 210. So that is 11/21. And we want to subtract the mean, which is 1/2. And that number is 42/1, so 1/42. And now we want to multiply by square root n because we want to make an approximately standard normal random variable on this left-hand side. So I want to multiply by square root n, which is square root of 21, divided by sigma. Remember, sigma is square root of p times 1 minus p, and p is 0.5, 1 minus p is 0.5. So sigma is square root of 0.5 squared, so sigma is 0.5. So that is greater than or equal to square root of 210 over 42 times square root of 0.5. No, sorry, square root of 0.5 squared. So times 0.5. So that equals, that is approximately probability that z being greater than this number. What is this number? That's 21 on the bottom, and on top is square root of 210. So that is square root of 10 over 21. And I can calculate that is approximately z being greater than 0.69. And that equals 0.5 minus probability that z is between 0 and 0.69. This probability we can look up from the table that we just looked up from. So we just look for 0.69 from the table. So 0.6 is here, 0.6 is here. So we want to look at this row and now look for 0.09 on the second decimal point. So that's this column. So we get this probability, 0.2549. So that's approximately 0.5 minus 0.2549. That equals 0.2451. Okay, so 24.51% is the probability that you observe a sex ratio at birth of 110 or more among this sample of newborns of the size 210. So that is not a tiny probability, but not a very high probability either. So we have considered two examples to use the central limit theorem to compute the probability of certain events. Now I want to consider like a trick question. Let's talk about this third example. So this third example is as follows. The death rate of COVID-19 is about 2% in the US currently. So it's lower now than at the beginning of the pandemic. And in the past week or so, 20 people in and around the White House has tested positive for COVID-19. The question is, what's the probability that they all survive? None of them die. We don't hope any of them to die. So what's the probability that they all survive? Well, how do you calculate this one? So suppose the 20 people, like we need to make assumptions, right? Because we don't have that much information. We need to assume that the 20 people are randomly selected from the US population. Well, clearly they are not because they are VIPs. But let's make this assumption. Assume that 20 people, these people, assume they are randomly selected from the US population. In other words, what we are assuming is that, so this might be a strong assumption, but what we actually need is just their probability of death from COVID-19 is the same as a random person in the US. A weaker assumption. Their probability of death or their probability of survival, their survival probability is the same as a random US person. Suppose that is true, and suppose they are all independent, whether they survive or not are independent, which is a much more reasonable assumption, which is a very reasonable assumption. Let's let their survival be denoted by xi, I from 1 to 20. So xi equals 1 if they survive, and 0 if the ith person survive, and equals 0 if the ith person doesn't survive. So xi follows a Bernoulli distribution of with probability 0.98, with success rate 0.98, because that is the survival rate. Then what is the probability that they all survive, meaning that the sum of all of them being equal to 20. So they all equals 1. So that is the probability that you want to calculate. How should you calculate this probability? You could calculate this using the central limit theorem approximation, but in this case, it might be actually better to just calculate the exact value of this probability using the binomial distribution. Because for the value 20, the PMM for the binomial distribution is in fact easy to calculate. So that's n 20 choose 20, 20 choose 20, which is 1. There's only one way to choose 20 from 20. Times p 0.98 to the power 20 times 0.02 to the power 0. And that is actually just 0.98 to the power 20. 0.98 to the power 20 is a value that you can calculate very quickly using your computer, which I can now do, is about 66.76%. So the probability that they all survive is actually not a very small one. It's not huge. There is still a chance that one of them will not, a good chance, actually more than 30% chance that one of them doesn't. But the chance of all of them surviving is pretty good. So this example is just telling you that don't use the central limit theorem whenever you see a sum or a sample average. It would be better to get the exact probability rather than the asymptotic approximated probability if you can get the exact probability. In this case, getting the exact probability is in fact easy. There is another thing related to this example is if you actually use the central limit theorem to compute an approximate value for this probability, you can do that, but that probability is not very close to this one. So which one should you believe? Clearly, you want to believe this one because this is calculated using the true distribution, not the approximate distribution of this sum. And the CLT doesn't give you a very good approximation for this particular event. The reason is twofold. One reason is that n is too small, and the other is the success rate is too close to 0, or 0.98 is too close to 1. When p is too close to 1 or 0 and the sample size is not too big, central limit theorem doesn't provide a very good approximation for the binomial distribution. And in the book, you will see some criterions for you to judge whether the sample size is big enough or not. And those are useful guidelines that you should have a look at.